if we want to go through some practice problems or something, we can do that too.
Okay.
So first of all, let's look at what a reciprocal function looks like. If we take the function, we'll call it p of x for parent function. That's it.
Mm-hmm.
So the characteristics are that it's got a horizontal asymptote on the x-axis and a vertical asymptote on the y-axis. And the most important point on the function is actually the point at 0, 0, because that's the intersection of the two asymptotes. Okay, yeah. And then it just goes through the point 1, 1, and it's got this reciprocal behavior where as x gets bigger, y gets smaller, and vice versa. Okay, and you'll notice it has this rotational symmetry about the origin. So if you rotate this 180 degrees, it lines up perfectly. Okay. Mm-hmm. All right. So this will be kind of a little Desmos tutorial as well here. Let's do this. I'm going to start a new function. I'm going to call it f of x. And I'm going to put in all three parameters for us. Remember what our parameters were. We had a was what we multiplied. That was the vertical dilation factor, right? So we have a times 1 divided by, and then h is what we subtracted from x. Remember, h was the x coordinate of the vertex. I mean, really, it's how far you've shifted it horizontally. Okay. We will make it, for convenience sake, when h is 0, nothing has been shifted, right? And so it's going to be the x coordinate of the rotational point. Okay, the axis, or the point of rotation, which is at 0, 0. And then remember that k, what we added at the end, k was the y coordinate of the vertex if there was a vertex. For us, it's going to be the y coordinate of the point of rotation. So all that stuff ringing a bell?
Yeah.
Okay. And if we want to look at another, I tell you what, real quick, let's do this. I'm gonna quickly just change this to, just to remind you how this all works. And for the sake of the video here, let's make this a parabola, just for a second instead, right? And then down here, this would have been, whoops. Oh, darn it. There, right? And now if I make all these 0, let's make these go by 1s. Okay, so this would be our normal. If I set a to 1, h to 0, and k to 0, nothing's happened, right? Because I haven't stretched it vertically. I'm multiplying, my vertical dilation factor is 1, so I haven't stretched. I've stretched it by multiplied everything by 1, right? So it hasn't been stretched and it hasn't been shifted. You remember this stuff. And so if I make a like 2, well, now look what I did. I just took the red parent graph and I stretched it up by a factor of 2, right?
Yeah.
If I make h something positive, so I'm subtracting 1 from x, then it scoots it to the right. If I make k -2, then I drop it down by 2. That's all familiar, right?
Yeah.
Okay, so now let's change the parent function to 1 over x. So I'm going to have to change this here. Go back to what I had before. Okay, same deal. If A is 1 and H and K are both 0, I haven't done anything to it. So you tell me then, what's going to happen if I make A equal to 0.5?
It'll be stretched.
It'll be stretched by 1/2, which means it'll be squashed, right?
Yeah.
All the Y values will only be half as big as they were before. Yeah, look what happened.
Mm-hmm.
See, they get pushed down. We have a point here. We used to have a point at 1, 1, and now we have a point at 1, and then 1 times 1/2 is 1/2. See what I'm saying? We used to have a point at 2, 1/2, and now we have a point at 2, 1/4.
Mm-hmm.
Okay, so there's one effect we can have. If I make A equal to something negative, like -2, well, now I stretched it and flipped it, didn't I?
Mm-hmm.
Right? So now instead of going over 1 and up 1, I'm going over 1 and up 1 times -2. So I'm going down 2. Okay?
Yeah.
Okay, the other effect then would be H is the horizontal translation. So if I make H, if I'm subtracting directly from X, in other words, I'm replacing X with X minus 1, then I just took the entire red parent graph and I shifted it to the right by 1.
Yeah.
Okay? And what might be helpful to look at here is how about if we look at the asymptotes as well? So if I graph the function, so there's my original asymptotes, and there's the point of intersection.
Yeah.
Okay. Okay. Now let's do the same thing for the blue function, right? And what we'll see here, if I just make I'll make the horizontal line y equals k, and the horizontal line x equals h. And let's do the point h k. Let's make these blue and keep track of what goes with what. And look what happens.
Yeah.
Okay, makes sense?
Uh-huh.
So if I make k -2, well, look what happened. Then the point of intersection of the asymptotes just gets moved down to there, and that's where a graph's been shifted.
Okay.
Okay, does that make sense?
Mm-hmm.
Okay.
Yeah, that makes more sense.
Okay, good. I will look. Have you noticed? Have you found all the resources I've been putting up on the Google Classroom?
Yeah, I saw them. Yeah.
Okay, good, good. So what I'll do is this video, whenever we're done with it, I'll make a copy of this video and put it on YouTube, and I'll link to that on a new page for reciprocal functions, and then I'll even maybe pull up some Khan Academy stuff, and if I can find some like a video from past years that I've made when I'm teaching this stuff, I'll link to that too. But does that help? I mean, do you think you can do it now, or do you want to go through a couple more?
Yeah, it helps. Just what happens when it's like 2x? What does that change?
Oh, they've got a 2. Okay, so
yeah,
I got you. Okay, so like give me an example of one.
It was like they're also changing the 1 on the top. So one of them was like -3 over 2x plus 2 or something. I don't know.
Okay, so well, the -3, that's the same thing. So like 2 times 1 over x is the same as 2 over x, isn't it?
Yeah.
So we could just as easily write this, instead of having the a out front, multiplying by a means you're just multiplying the numerator by a.
Oh, okay. That
Okay,
makes
see what I'm saying? And then, so what if they had something like you said, for example, they had, let's go to, here, let me turn all this stuff off for a second. Turn this off. So they had an example like, you just tell me one that they had. So what if they had something like h of x equals, you said -3 on top?
Yeah.
Divided by
2x,
2.
I think, plus
Okay.
minus 2, one of those.
Let's say 2x plus 2, just for an
Yeah.
example. And then at the end, they had something too?
I don't
Just
think
that?
so. No.
Okay, just that.
There
Okay,
are
so
a bunch of different kinds, but
okay, so there's a bunch of stuff you can do here. There's something called a horizontal dilation factor, which is what you're multiplying the x minus h by. So there's a couple ways you can do this. I'm kind of surprised they did this, honestly. So one way I could do this is I could go back up here to my original. Let's go up to our original. Oh, what did I do here? Oh, I know, I can't have h. I gotta make that something like g. I already have g, don't I? No, I don't. Make it g. Okay. So if I go back up to my original parent graph and I'm going to multiply the quantity x minus h, I'll show you something cool. This is probably not what they had in mind. This is a little harder than what they had in mind, but it's you'll like this, Lucy. I'll show you this. So if we multiply by 1 divided by b, okay, and I'm going to add another slider for b here. Let's see, let's go. Oh, darn it. -2, tab 2. There we go. Okay, so now let's look at the effect of this. Okay, let's look at the effect of this then. So if we go back to make everything, let's kind of reset everything here for a second. So A is 1, H is 1, H is 0, sorry. K is 0. Okay, so we're just normal, right?
yeah.
Okay. Now watch what happens with B. B is, if I multiply the reciprocal of B times the quantity x minus h. If I make b something like 2, now what it did is it took this point and it stretched it horizontally by a factor of 2. So instead of going over 1 and up 1, that point has been stretched a horizontal distance. It used to be 1. Now it's been stretched to 2.
Mm.
Okay, see what I'm saying?
Yeah.
Okay. And so if I make b something like 1/2, then now when I go for a vertical distance of 1, we'd normally expect a horizontal distance of 1 for our function from the origin, right? Now when we go up by 1, we have dilated the horizontal size of the function. So we're going over 1 times 1/2.
Yeah.
Okay, does that make sense? So then if we do something like this guy right here, what's going on here then? This is saying that for this function right here, if I were to, I'm talking about this guy down here, right?
Mm-hmm.
Okay. So we can see that A is -3, isn't it? Right? The negative out front gets multiplied by the 3 on top. And so we'd prefer to maybe even just write it like that, right? So we know that one thing that's going to happen is this thing has been vertically dilated by a factor of -3. Okay.
Yeah.
Now on the bottom, I've got it. What is being multiplied by x minus h? Well, if I factor a 2 out of this, this is that 2 times x plus 2 is the same thing as 2 times the quantity x plus 1. right? Okay. So then that tells me that H is -1. This thing has been shifted to the right by -1, which means it's gone to the left by 1. Okay, which makes sense. If I look at the point of intersection now, see where my pointer is? It got shifted. The purple function got shifted left by 1, and it's been stretched by -3. Instead of going from that point, instead of going over 1 from the, from my reference point and up 3, or up 1, sorry. Instead of going over 1 and up 1, I'm going over 1 and up 1 times -3. So I'm going over 1 and up -1, 2, 3. But you might be saying, well, the function's not there. That's right, because it's also been horizontally dilated. 1 over b is equal to 2. So b in this case would be equal to 1/2. Okay, so if we want to overlap this purple function with our blue function, what values are we going to have to set for a, b? And I'm going to stick b down here, so it's, there we go. What values would I have to set for a, b, h, and k? Well, you tell me. What would I have to make a if I want the blue function to become the purple function?
The blue, for a, it would be -3.
Exactly. Okay, so let's do that. We'll make that -3. B would be what?
1/2.
1/2, exactly. Okay. H would be
-1.
-1. Good job. And K would be
0.
0. And look what we did. We overlapped it.
That makes sense.
Okay. Now there's another way to do this. So that's one way. That's pretty cool. Okay, but there's another way. You could also, if we go back to our, you had 2 times x plus 2 on the bottom, right, without any parentheses. Okay. This is the way that I would probably, like I didn't do this stuff with my regular class. I just did this with my honors class.
Yeah.
Anytime you have a horizontal dilation, would you agree that a horizontal compression is really the same thing as a vertical stretch?
Yes.
You see what I'm saying? The effect is the same, isn't it? Right?
Yeah.
So what we could do here instead is we could, if we want to be really tricky about this, we could just pull, like we could factor a 2 out of the bottom like we did before. I'm going to make a new function down here. I'm going to call this one j of x. Okay, and we're going to have our -3 on top. But on the bottom, I'm going to take that 2 and I'm going to factor it out of the bottom, so I have an x plus 1 on the bottom. Well, really, that's the same thing as saying I could just, instead of multiplying by 3 and dividing by 2, is that the same thing as multiplying by -3/2?
Oh, yeah.
You see what I'm saying? So I could just make this on top. I could make this a -3/2, and think about this as only being, and let me change the color of this so you can see that it's the same thing. Look, well, that's a bad color. Make it green. See, look, they match up perfectly.
Yeah.
You see what I'm saying? So you could really take your pick on that, whichever one you wanted to do. Personally, to me, I think the bottom way is an easier way to deal with it. You really don't ever have to invoke that horizontal dilation factor. That's one that we don't typically use. And so it's almost easier just to figure out, what am I multiplying the function by,
Yeah.
Okay. So what else? Any other weird problems they gave you?
Just like, so to find the asymptotes, the y one would just be h, right?
Yeah, exactly. The y is always going to, well, no, the y would be, you mean the vertical asymptote you're saying, right?
Yeah.
The vertical asymptote would always be the equation x equals h. Exactly. Right. And then the horizontal one would be the line y equals k. And you know that because the asymptotes are the lines that travel through and intersect at the point of rotation.
Yeah.
So in this case, you tell me then, without looking at the picture, the graph, what would the equations of the asymptotes be for the green function?
-1 and 0.
When you say -1, you mean you're saying that x equals -1 and y equals 0, right?
Yes.
Yeah, exactly. Yeah.
Okay. I think that was it. It was just kind of weird. I don't know.
No, I get it. Yeah, I get it. Yeah. And I'll make some, so I guarantee if you're having questions on this, everyone's gonna have questions on this. So I'll make some resources for people to look at that might be maybe a little better than what he's doing, I guess.
Yeah.
All right.
Yeah.
How's the rest of the stuff going? Seems to be going okay for you.
Yeah. Otherwise, I didn't have any other problems. It makes sense. So.
All right. Well, good. Well, it's nice talking to you.
Yeah.
Outstanding. Well, I'll go ahead and post this if you need to refer back to it. And just if you have issues on anything else today, just email me. I'll be checking my email.
Okay.
All right. Well, hey, you have a good one.
You too.
All right. You betcha. See you, Lucy.
Bye.